I think we should just go ahead and get started. So, this is a topic that we offered last month, but there were some technical issues with the Zoom link that we have since resolved with Aaron's help. Really appreciate that. So we're moving forward, and we actually had a speaker lined up who canceled at the last minute, but graciously, Jehren and Keane were willing to fill in and touch again on this topic of LoRaWAN Framework Adaptations for Science Workflows. So Jehren is a graduate student at the University of Nevada, Reno, and Keane is a research engineer with the Nevada System of Higher Education, and they've been doing a lot of great work with LoRa in mountainous environments. And I'm just gonna send it over to you guys.
Thank you, Renee. Yeah, so I'm Jehren. I'm a PhD student at the University of Nevada, Reno, and I originally um, uh, started my academic career in paleo science, climatology and dendrochronology and such. And Scotty scooped me back up for my PhD in a whole different realm of in situ measurement monitoring with this funky long acronym, LoRaWAN, which took me a long time to figure out what it is, what it does, and how it's incredibly powerful. And yeah, I like to start off with our Sherman name. I'm sure everyone has been past a semi truck with that logo on it and kind of scratch their head, and you know how strange of a image that is. But it really stuck with me because LoRaWAN is kind of this thin layer that I feel like should be everywhere, all over the earth, filling in all these gaps that satellite remote sensing and other in situ monitoring networks aren't able to do. So you can see here in this little um, graphic above the earth here is that we're so used to cellular and Wi-Fi, but those kind of fill this big gap of long distance and low bandwidth and low power that LoRaWAN covers. Wi-Fi, cellular, Bluetooth, short range, or incredibly expensive investments to create a network that other people can join in on. So LoRaWAN does have this cool, very open source ability to allow communication between IoT devices in pretty wild and formidable terrain. What's our next slide, Keaton? So LoRa and LoRaWAN, it seems like often more and more we kind of use LoRa as a abbreviation for LoRaWAN, but they are indeed two separate things, right? LoRa is the modulation, demodulation of data into RF propagation. And it's super nifty how it takes these frequency modulation, like you get on your FM station, but has them metered into certain up chirps and down chirps of ramp. So ramp can then be um, shortened, lengthened, and chopped up in different ways to create your bits and bytes that are part of each payload. This little graphic in the bottom left, where you can see these SF spreading factor. You can see that most everything is an up chirp. The down chirp is used as kind of a um, signal of between a preamble and a payload, so that a gateway, a receiver can start listening correctly and have all of it indexed for a proper payload. And this is actually the really cool thing in this IoT realm is that these spreading factors can be utilized by these different sensors to encode these payloads and send them to any receiver that's listening in range. And they can overlap each other and not conflict. So at the very bottom of that, you can see this nice neon scribble of these different spreading factors that over on top of each other. And there's a lot of back and stuff. I still have a lot to learn about of how these are able to negotiate and not conflict with each other and pass into the gateway and into the TCP/IP network. then that's part of the LoRaWAN, right? So that's the wide area network of the long range abbreviation. And the LoRaWAN is LoRa added to this wide area network. So we can see at the very bottom right our little infographic here of all the sensors, all the gateways, reaching out to a network server and the application server where you can find all of that data that's passed through from the comfort of your office or even in your couch. And above that is all of those big numbers that create these pretty incredibly secure layers to encrypt the data from these payloads at several different levels um, and transmission types. Keane will talk a little bit more about that later. And let's go to our next slide, Keane. Okay, so Laura, what's the long range for us? 10 to 15 kilometers is what is advertised in all of the providers of hardware, the LoRa Alliance, that does manage the protocols across LoRa. And so I got a couple examples here, right? Bottom right, this is kind of one of our first installments I'll talk a little bit more about in a minute. But I drove around with a sensor strapped to the top of my Subaru and kind of started collecting these values. And 8.5 kilometers away, kind of high point to high point, 80 negative 87 RSSI, which is an incredibly strong signal for LoRaWAN. And 45 kilometers from ridgeline down to a valley bottom, negative 120, which is pretty okay. And the record that we currently hold, that Keane has set from a mountaintop down to a very rural trailer. Most people think be in the middle of nowhere. Yeah, 72 kilometers at negative 125, which is getting pretty weak on the connectivity there. And I even had one in kind of one of my testbed sites above my house, not past that. The transmitter fell down off of a tree in a forested area and it fell into a tree well, and the antenna was aiming towards the ground. It had 6.5 kilometers down to my gateway at my house. It still had a pretty strong signal. So we've been continually impressed with how good of coverage we can get in seemingly marginal conditions or just very long distances. And we got tons of stories about all that. I won't go through all of them, but it's very impressive so far. Let's go to our next slide again. So use case study here is what I first hopped onto this PhD project. I was looking at using LoRaWAN as a possible um, possible citizen science platform. And we learned a lot from this one, right? This is an off-the-shelf solution, right? We got gateways that merely passed data through to whatever TCP/IP connection it could get, Wi-Fi or LAN. We did a point-to-point shot to the State Science Network up that has a node up at the ski resort to the left. There's yellow square to yellow square. And just a small little Campbell Scientific station with a solar panel and a battery, a router, and probably a little bit more equipment than we need nowadays. We have a red circle and a green circle on that mountain across the way, and those are kind of two comparative slopes that decided to put soil moisture sensors and temperature sensors, and just do kind of a comparison of these heavily burned, high severity burn slope, high elevation, low elevation, versus a low severity intact canopy slope, high elevation, low elevation. Just try to capture some of the metrics of snow timing, accumulation and melting, and as well as currently we're capturing soil moisture properties throughout the summer. So bottom right, we can see in the blue, that is the Campbell Scientific data logger that captured, that's actually battery voltage. And in the red, we have the LoRaWAN packets. And I believe many of you can see these very large gaps, which came either from loss of power at the site network issues on the Nevada seismological side, um, security permissions, back end updates, stuff like that. It was just, a little bit on my pay grade and other people that were not communicating clearly about the network itself would allow instances where data would not be subscribed to and would just drop into the ether. So a lot of lost data, but you can see here, April onwards, we have pretty solid data. No gaps in that as well. So we can take a look at that and go to the next slide, Kean. Right. So when we have some network stability and we have data that is not gapped, right, we can see some environmental phenomena happening. And I didn't put any photos of deploying those 4 sites, but I did just have a backpack and some of these sensors, a couple poles and a hammer, and I was able to put out these sites, which each sensor was around $100. So each site was around $300, give or take. And I was able to deploy that in 2 separate campaigns, a day by myself, taking the dogs for a walk. And they're going to be there for several years collecting data. And with a stable network, we'll be able to capture that and do some good comparisons. All right, Keaton, let's go to our slide. So off the shelf turned out to have some issues. Offline caching did not exist in that framework. And that gateway was passing any LoRaWAN data that it heard and passed it along. And our power at our site and the other mountaintop sites, right, was the issue that needs, more addressing to make sure that the network is more resilient and the data that may or may not make it can be cached and is not lost instantly. And this is a new project that we just kicked off this year, joining up with some hydrologists that are looking at forest thinning impacts to soil moisture. And you can see all the red place marks are a bunch of sites in which field science has been done for a long time. They're planning to use SneakerNet to go out and collect data manually, do transects, install some Campbell Scientific data loggers that will need to be manually downloaded onto SD cards, USB drives. And Kean and I joined in and added a couple sensors. And this measurement you can see from Babbitt Border Gateway, and that yellow line straight up to the site that we put in. And that's at 19, almost 20 kilometers with some geographic features in the way and a lot of forest cover. And we were still getting some mostly reliable data transmission around negative 120 RSSI. And we are waiting on some permitting. It's pretty much there. We're going to go put a repeater gateway in between that to increase our resiliency of transmission. And these newer gateways that he has provisioned, he was able to put in some very nifty middleware to allow for capping when network goes down. And this is kind of our version 3, I would say, of trying to make this off-the-shelf implementation a little more custom so that scientific payload could be entrusted to this network. And I think I'll pass it off to Keane here. I think the next couple of slides are ones that he put together.
Thanks, Jehren. Hmm. Second, let me see if I can get that to reload. Maybe not. All right. Well, hi everyone. For those of you who haven't met, my name is Keane Flynn. I am a field networks research engineer for the Nevada System of Higher Education. I've been helping, or Jehren has kind of gotten me indoctrinated into this world of LoRaWAN, something I was entirely unfamiliar with a year and some change ago. And since then, we've been trying to fill in a lot of these gaps that and shortcomings that Jehren has identified through his field work. That's really the only way to figure out what's wrong and how to build upon it. So um, we kind of wanted to go through step by step, all the parts along the way here and figure out what shortcomings we really have and how we can address them in kind of taking more of a enterprise or industrial approach to these engineering tactics that have been used in industry for a while and apply them in the research sense, but also apply them in a way that really still works for people like environmental researchers who may not be the most tech savvy people on the face of the earth, but still really need to and definitely can reap the benefits of what LoRaWAN has to offer. So with that, nice addition there, Jehren. We kind of wanted to adopt an architectural ethos going into this. One of my favorite kind of design principles is from the car company Lotus back in the day. Their founder and team principal always said, "Simplify, then add lightness," and I really enjoy that because it just kind of embodies making things that are digestible, easy to diagnose, easy to understand how everything is working. So with that, we kind of had a core four principles that guided a lot of our decision making here. So number one was identifying robust tool chains and design concepts. As Scotty and Jehren can certainly vouch for, we have purchased a lot of different pieces of equipment and looked at a lot of technical data sheets to figure out what exactly makes all of these pieces of hardware tick, all of the software stacks we decided to adopt for this. We spent a lot of time digging into it and seeing what is as close to industrial as possible without adopting an industrial price tag for everything. So with that, making sure that we stay in the right ecosystems to support this and kind of fill in these weaknesses that LoRaWAN inherently has was step number one. And then number two, and this is kind of a really big one for smaller organizations, is to place the maintenance burden on others. I'm sure anyone else who has worked in a smaller team can relate with this, that having to maintain every step of your tech stack is really unsustainable. So making sure that you're picking steps of those or pieces of those tech stacks that are very commonly used, well open sourced, good documentation for, and that receive frequent updates and yeah, just are very well documented is a huge part of this to ensure that you're not having to do full architectural updates every year to what you are what you're applying in your whole system architecture. Step number three for this was reducing the dependency chain, and for a very similar reason that as dependencies change, as there are little as people are tinkering with whatever it is that is embedded within your workflow, that tends to break things. So reducing that chain is really important to making sure that this is something that is maintainable. And the last part is to reduce parts when feasible and eliminate them when possible. So this is really just kind of going down to simplification. And this applies to both hardware as well as software. So as you'll see when we go through step by step of each piece of hardware here, this is we tend to reuse parts as much as physically possible so that we don't have to go sourcing parts from a bunch of locations and one part source might dry up depending upon, manufacturer and supply chain, that sort of thing. So, and with that, let's kind of get into the stack we're working on here. Okay, so starting with our sensors. So there are a few core companies that produce LoRa sensors. These are probably the four that I've seen that tend to be the most mainstream. Seed Studio, Dragino, Milesight, and Laird. These are in no particular order. We have been using Dragino sensors with uh, very solid reliability from the devices themselves. They are a little less feature rich, which also places them lower on the range that I have quoted here from about 100 to $500 a sensor. For example, an air temperature sensor from Dragino that is outdoor rated will run you about $85. So um, we are currently testing those to see how they work compared to against a Campbell Scientific air temperature sensor. So it's kind of the golden standard for measuring air temperature. So, and then if you want to go on the higher end of cost for this, companies like MileSight produce what I would call very industrial grade that you can calibrate sensors and ensure that they're within spec. So. These devices are also very impressive as far as footprint versus their power supply. So they generally last on, assuming about hourly transmissions, you're looking at about a 5 to 10 or more year lifespan for these devices with just the 18650 battery located inside of them. So, and then for the one in the picture here, those of you with sharp eyes can probably see that as a solar panel on the front board. So it is able to recharge battery, and we're just looking at battery degradation as far as what's going to kill it off over time. So additionally, all of these devices will give you configurable transmission specifications, as Jared showed in the beginning. Those with that graph of different spreading factors, those are able to influence your ability to penetrate through things like tree canopy, and can give you a little bit more distance on transmissions depending upon how much data you need to transmit and how much power you are interested in saving from the device on each transmission. So, and as Jehren quoted, personal best we've been able to get out of this is over 70 kilometers, and that's with an omnidirectional antenna. Swap that for a directional Yagi or something cheap, like a log periodic, and you're probably looking at 100 kilometers if you're going with unobstruction or without obstructions. So these devices in the US use the 902 to 928 megahertz ISM band. There are some that are available in 433. Those are going to use more power, but can help you get more distance and better penetration through forest canopy, that sort of thing. Additionally, as Jehren referenced, we're going kind of had to go through a minor like asking permission for putting some of this stuff out. It is very easy to convince the BLM, Forest Service, whomever you might be working with, that the entirety of your footprint is a single T-post in the ground. And even if you don't want to have to do that, a ratchet strapped to a tree will have virtually no footprint whatsoever. So a lot of good benefit. All right, and then on to the next part, which is relaying data. As Jehren pointed out, sometimes you don't have, you're not within 30 miles of internet connection somewhere. So with that, we can use relay gateways. Apologies for the stock image, don't have one of these out in the field right now. And all these devices basically do is ingest packets coming from LoRa sensors, encapsulate them with this device information, and then bounce them on to the next relay that they find. These are capable of doing up to 8 hops to stay within the maximum packet size. So you can transmit up to, so you can bounce up to 8 of these between gateways, so then you can get a 9th one to the last hop. As you can imagine, if you're looking at 30 miles pretty easily from hop to hop, at 8 or 9 of these, you're getting over 200 miles if you have blank area. So these devices are also incredibly impressive. They use less than 2 watts of power under load. That allows you to maintain a pretty small footprint as far as having a battery attached to it and a very small solar panel. We are adopting 50-watt panel and a 26 amp hour deep cycle battery. This is way overkill for these and should keep them online for about a week with absolutely no sun whatsoever. So, and again, these devices use no actual TCP connection. They are simply there to functionally amplify a signal and send the packets along. So yeah, and these devices run about $250 for the device itself, and for how we send them in the field, $700 a pop. So all right, and then we will eventually get through all of our hops and get it to an actual internet connection, and that's where we have our border gateways. These are also a rack wireless gateway. The benefit of using this company's, after having looked at a number of different companies that produce these, the benefit of Rack specifically is they work with a software development group called ChirpStack, which I'll get into in a couple slides here, to actually custom develop an operating system for these gateways, both for the relay gateways and the border gateways. And this allows them to interface with your LoRaWAN network server really easily. See that LNS acronym in there. And this is what enables this sort of mesh architecture, which is not a feature that is available for other LoRaWAN hardware. So this provides a huge benefit to us, and this company actually works directly with the third-party ChirpStack organization to maintain a custom operating system for these that is functional. So these border gateways use just under 3 watts of power under load. And as Jehren touched on, the kind of secure aspect of LoRaWAN, all of these gateways have the 128-bit mesh network key that will basically ignore any packets that don't have this key with them, so it can limit your network to be private. And to touch on the actual aspect that Jehren identified as one of the biggest weaknesses is the offline caching. In order to address that, another huge benefit of these devices is you are actually able to play around with the operating system on it and sideload whatever applications you want. So for this, we developed a custom Go application that you're able to cache LoRaWAN packets in a bbolt database and will replay to the LoRaWAN network server when it gets reconnected to the network after its outage. And to actually ensure that the device stays powered on during this whole period, because if either your router goes offline, then and that's where your power source is. It doesn't really matter if you can cache if the device is turned off. So what we did for these is we were able to create a hardened power configuration that has redundant power supply from the router PoE, and in addition using, again, a 50-watt solar panel and a 14 amp hour battery. So this generally consists of a small charge controller, 50-watt panel. The Victron ecosystem is really nice because it has integrated low voltage disconnects, so that'll save your battery if you do dip below whatever threshold you set. We tend to use 11.5 volts. This power coming from the PoE router is kind of merged with the standalone power from our power system here into a diode or ring. So this allows for seamless power switchover and minimizes moving parts that usually relays have. So you can expect a better life expectancy out of these sort of devices. And if the router dies, it switches over to our power instantly, and we are still caching data at that point. So additionally, we also have a few lightning protection units to isolate our devices from the supplying router and from our gateways, so that we're hopefully don't have all of our equipment nuked at one point. And then actually getting this data back, as Jehren pointed out, the Nevada has a really impressive and extensive state research network that is maintained by the Nevada Seismological Lab. This is a map of everywhere we have in Nevada at the moment. As you can see here, it's a pretty good coverage of area here, and as I pointed out, that kind of like 200-mile metric I said that you can cover with these network repeaters is there's basically not 200 miles of distance between any two of these points. So in theory, placing these strategically can allow you coverage for most of the state. So, all right, and then from there, it's just a matter of getting it back to our LoRaWAN network server ChirpStack that we're using that lives in our data center here at the System Computing Services facility in Reno. And all of this basically is just run through an MQTT broker that the encrypted packets, as you can see, in the terminal output here come in, they're decrypted and then sent through the MQTT brokers. So at this point, it becomes just a very standard and well-documented procedure to ingest MQTT data. So just kind of in this whole process, all the LoRaWAN network server serves as a way to ingest data, decode it, decrypt it, and republish it to wherever you are choosing to uh, store this data. And I will show that we kind of go a little bit of a custom route here. But for those of you who are not interested in something maybe a little more uh, tweaked and configured for performance and scalability, for example, right now we're running this just with a vanilla plugin to InfluxDB, and it is working perfectly fine. And we reliably have data transmitted to us. So yeah, ChirpStack's very good for that. It's very feature rich and allows you to configure your integrations very well. Um, yeah, so can't recommend it enough. The other option for this that we've used in the past was the Things Network, a little less feature rich and requires a little more babysitting. Um, so we've found that there's just generally a lot more benefits to this in addition to the native integration to the gateway operating systems. So. All right, and then once it actually gets to our back end, this is kind of the architecture and hosting model that we are currently planning on adopting. Um, so our MQTT data stream is massaged by a Go application so that it's just formatted nicely and then is ingested by a Telegraph broker. And then all of this data is then sensor data as well as heartbeats from the gateways, which serve as our kind of I serve as our metric for uptime. These are collected and stored in a timescale DB relational database. So this is optimized for really fast read writes for hot sensor data, but still maintains being a relational database so that these can all be easily, all these devices can be easily managed and onboarded. Yeah. And kind of moving forward for the future, we plan to have our undergraduate students develop a custom dashboard so this data can be displayed geospatially and also have an alert system for when things go offline so we know how to get in the field and minimize our downtime. So, and then our general model for this for organizations that are interested is going to be that we'll offer hosting services in exchange for this data being public data. So part of the dashboard will be that it's easy to download and people can start playing with it however they want to at that point. All right, more future plans. We also would hopefully not have to onboard every single sensor at a larger scale. We would be able to create a portal where with an identity access management integration that our team has been working. I say our team, it's mostly Garrett, has been working very hard on. So having that would be a very nice feature to scale well. Additionally, we do plan to open source this tech stack with Ansible and Terraform set up so that if anyone out there wants to host all this privately, they totally can. And additionally, we are hoping at some point that we can integrate this from our existing DMZ on our research network to our production VMware. And hopefully, if our team gets this figured out, Kubernetes cluster so that we can have a better high availability model. Additionally, a lot of our student or undergrad researchers tend to be electrical engineers. So we're hoping that we can also do some in-house development and open sourcing of sensor designs to meet the needs of scientific community and researchers. Yeah, so this is be for hydrology, fire, wildfire, mountain science, whomever is interested. So. And then last but not least, more coverage. As Jehren said, cover the earth. We have a remarkable opportunity here in the state of Nevada and beautiful topography to support being able to have some pretty impressive coverage of the state. So yeah, getting those gateways out and adding sensors to them. That's really what we're hoping to do here. So yeah, that's about what we got here. So.
Yeah, thanks,
Yeah.
Kian. I mean, I think it's just this is presentation is just a great example of the power of having your own personal research engineer available as just a grad student that is not super steeped in technology and software and that. I certainly was struggling to um, swallow everything that LoRaWAN had to offer in a lot of the security and back end and integration into all these other um, open source software platforms and such. It's pretty amazing that I get to just dream up a way to get the sensors out there, and um, Keen is able to help make that more of a reality and better, safer, more redundant pathway for the data to make it back home. But yeah, so we were told that we were trying to open this up as a discussion. So I guess we can uh, hear from the crowd of anyone who had some interesting thoughts or comments or anything of the sort.
I've got a question. Hi, I'm Carl. I'm in New Zealand. I'm a research software engineer at the Bioeconomy Science Institute. Um, you mentioned that at one point you mentioned data was going into InfluxDB, but then later on you mentioned it ends up in timescale DB. I didn't quite follow how those two different time series databases fit into the system. Can you explain that a bit better, please?
Yeah, definitely. So currently our just version one of this that we're running is just running directly into InfluxDB. There is all you have to do in ChirpStack is give it an API key to Influx, and it'll create your whole database schema for you and just start writing instantly. Very straightforward. We're using that right now kind of as our production system. However, we are probably about a week or two of work out to migrate that all over to timescale. So that's kind of just in our testing right now. It does provide a lot of benefits unless you are interested in paying for influx. So our goal here was to, yeah, again, keep everything as open source and free as possible for other people to reproduce this. So yeah, that was the direction we're choosing to go with this. So a lot more configurable to stay in the Postgres ecosystem.
Thanks.
So, Jehren, once you have a one-page instruction manual for your colleagues in the sciences or citizens that might want to take advantage of a network like this, how easy is it, do you think it will be for them to procure a sensor, get it running, and access the data? Let's assume for a second that a web portal for the data exists. But in terms of the hardware and the provisioning piece, right? How do you think this is going to be straightforward? Or do you think it's going to be frustrating? You're going to have to constantly address like Slack messages or emails or something.
Well, I'm glad that you put in um, the idea that there is a portal, which is on the way. I think that that's certainly going to be the inflection point of people buying into the system is the fact that they can just open up a web page and get right at it. Um, Currently, yeah, it takes a little bit of typing to take some of the data from the box and, put it into you got some big numbers there in the box. You got to put it into the chirp stack and get it onboarded. But that's also in the works is to that our amazing research engineers are looking at how to actually um, pipeline that into a online um, I don't know what do you call it in your
Yeah. So I suppose another selling point for ChirpStack is it has a very robust API layer to it. So someone submits all of the necessary credentials to us, and then all we have to do is, thumbs up, thumbs down the addition to it, and we can post that to ChirpStack, and it will automatically accept the device. So,
Yeah,
yeah,
so barring just a couple portals away, it should be very easily accessible to anyone who is able to purchase the sensor um, off of a website and can get onto their computer and reach our online portals, and that can go right into our system through ChirpStack into our server. And like Ian said, as long as that data becomes publicly available, we can broker those services um, to keep the data here on our server. But yeah, I certainly had to deal with a little bit of a headache doing it before Keane joined our team. It was certainly a little more requires some more tech savvy understanding of how to set up all of the uh, MQTT publishing, subscribing, and making sure that every single character is absolutely perfect, zeros instead of O's, such like that. But I think with a couple more tools that are created, certainly it would be a pretty painless experience to purchase them online and run them through our system.
So speaking of the different things, what's the breadth of sensors you found so far that utilize LoRaWAN?
So I'll say that we have certainly leaned on soil moisture as a measurement, mainly because soil as a medium slows down the response time for temperature and moisture. That and it touches all of the parts of most ecosystems. So it has proven to be a good measurement since it doesn't require absolute accuracy comparable to other sensors, and its power is a little bit more in the length of the data set that you accumulate, and it becomes a little bit more comparative to previous measurements rather than being an absolute number. And we basically just stuck mainly with Dragino just for the price point, and we haven't gone too far outside the realm of Dragino soil moisture and temperature, mainly because we are advantageously looking for opportunities to compare them to other sensors for benchmarking. Other scientists that already have data sets that are ongoing that we could co-locate with just to see advantageously how well these sensors compare. So we're doing that a lot with temperature now, and the project that I brought up, well, we're going to do that with Campbell Scientific soil moisture probes and some other inexpensive ones to try to get just a better baseline. But we are also going to spend some time this summer and next semester with our undergraduates looking at custom builds, mainly interfacing well-respected sensors with converters and transmitters that are, Dragino LoRaWAN, and seeing if there are any issues with taking a high-quality sensor and integrating it to just a LoRaWAN transmitter.
Yeah, that was kind of my question. That like I noticed there's only one that I found, Decent Lab, DECENT Lab, Swiss company. They have a temperature sensor which is CE certified with European safety and EMC directives, which I think the USGS is completely ignorant of or does not care, right? Because I think it's the NIST standard. But that seems to be what maybe you're addressing, Jehren, is the Achilles heel of LoRaWAN, at least for scientific use, is the calibration of the sensors. Because like your average IoT person, they don't care, it's the layered temperature sensor, for $75. All right, so that's where we fell into kind of a little bit of disrespect there for the layered temperature sensor, So,
Uh,
and then if you've got people, especially if you've got people like with Keane, like programming the platforms like ST Micro or like you said, Dragino, sounds like you've been led down into this path where you're going to have to do your own integration, right?
Um, yes and no. So,
Mm.
com at least Dragino, they offer two different devices. They offer one that
Mm.
is just straight up you bring your own sensor that is either SDI-12 or RS-485, and you can plug it right in. And then when you need to send the actual device itself off or the sensor itself off to be calibrated, same process. So that will work for a bunch of Campbell Scientific equipment. I at least know off the top of my head that their air temp sensors and soil moisture sensors all operate on SDI-12. So those two or Dragino makes that, MileSite makes that as well, with a little easier of a setup process. But yeah, no, you've absolutely identified one of the. I'm assuming what is going to be one of Jeren's chapters of his PhD is the comparison point of accuracy between what is, industrial grade and what is, just going to be an IoT device like this. And then at that point, kind of putting that information out there and figuring out this sliding scale of, all right, so if you want a telemetered Campbell Scientific, very industrial grade sensor, it's going to be the air temp sensor, then it's going to be your data logger, then it's going to be the radio connection, then it's going to be all of the solar to power this more high-powered equipment. And it's kind of this, all right, you have a telemetered Campbell station for, $5,000 or something like that versus this very opposite end of the spectrum of 100 or $200 for a LoRaWAN sensor. And where do you want this sliding scale to be of quality versus cost, which is certainly in the hands of the researchers to answer that question.
Yeah, and that sliding scale does also include, spatial application, right? How many sensors can you afford to put out there? Where can you put them out there? And would lower a lower amount of accuracy per each sensor offset be offset by the amount of sensors you could put across a geographic area? And it all comes down to the science question, right? Like I don't believe that these LoRaWAN IoT low quality cheap sensors are going to completely replace the sensors that we respect and know. But how can we augment that and answer different science questions that those high accuracy sensors just, it's just not feasible to use them to answer such a widely spatial question. So yeah, I think I keep looking at this as how can we do more with less, right? Let more spatial coverage with less bandwidth, right? More access to different science questions to answer with less cost. And yeah, it's a sliding scale. I mean, it's just like all those triangles that you could say, right? And computer engineering of durability, cost, and yeah, choose two of three that you can actually reasonably
I
attack.
think Purple Air, I think, is a great example. They managed to take low quality sensors and somehow promote it as a standard within
Yeah.
EPA, even though it's proprietary. Also,
Yeah, I'm really interested in the future of integrating an off-the-shelf LoRaWAN framework transmitter slash controller with the more smart self-contained, SDI-12 type sensors that we use with things like Campbell data loggers, so that you can be deploying a standard. The question comes down to things also like, a lot of times when we deploy a Campbell logger, we'll be doing a program scan every few seconds, right? Depending on what your application is. You'll be aggregating those data, really making it smooth, even to the minute scale. Whereas with something like LoRaWAN, where we don't want to power everything up except for once an hour if we want it to last for a really long time or whatever that interval is. So then you're just getting a point measurement. So the curve isn't nearly as smooth. And so there's going to be this interesting distribution depending on what it is that you're measuring, that is more or less applicable at different time scales. And so, maybe, hourly LoRaWAN observations might be good for, twice daily or the daily extremes or whatever, but it's not going to be as good for, the actual 60-minute, even if that's the data that you have, because the sensor only took one measurement and sent it out. So then there's going to be people that want to play in between with the very low power microcontrollers and be able to do some smoothing and aggregation locally before you send out the point. And then how big is the battery and the solar panel for that? Like, this community could get really creative in that space. And so, like, I feel like that's kind of a future. There's a lot of interesting things to be done there.
Great.
Thanks for
Well, oh, I'm
sorry. I was just
sorry.
going to thank them for all their good stuff there, and say I want to hear about hooking it up to a Campbell data logger just as a back end. Anyway, but full speed ahead. I guess we're at the end of time.
Yeah, I was gonna wrap it up, but yeah, I'm really interested in that too, John. I've been interested in that for a long time, so I'm looking forward to seeing what you guys come up with. And just another comment, kind of adjacent to what Scotty said. So thinking about time, not just measurement frequency, but how long you might want those sensors deployed. And I know that's not going to be part of your dissertation because you don't want your PhD to last 10 years, but a lot of the work that I've been involved with using sensors, like we're running these things for 30 or more years. And so using Campbell is like the way to go there. And it'll be interesting to see how long these other technologies can last. But yeah, this has been a great discussion, and it sounds like we could probably go on for at least another hour. Um, Maybe we can take it to the Slack channel, but for now, I think we're gonna end it here. We're at the top of the hour. Thank you very much, Jehren and Kian, for coming in at short notice. Looks like David has an announcement. You want to mention that real quick before we end?
No, I was just going to reference the earlier demonstration about down sampling using this product like on an ST micro type of platform.
Cool. Thanks for sharing that. Yeah, and be on the lookout. I'll send out an email about our new office hours that are coming up later this month. Join the mailing list, join the Slack, and we'll see you next time. Thank you.